Okay, great. Good evening, everybody. Thank you for joining at this time of the day. Uh, I'll start off by introducing Professor Angel, and then we'll start his session. Professor Edward Angel received BS from California Institute of Technology in 1964 and MS and PhD from the University of Southern California in 1966 and 1968, respectively. He has held academic and visiting positions at the University of California at Berkeley, the University of Southern California, the University of Rochester, Universidad de Los Andes, Venezuela, Universidad Tecnologica Equinoccial, Ecuador, IISc Bangalore, Imperial College London, University College London, and at Los Alamos National Laboratory. He is currently Professor Emeritus of Computer Science at the University of New Mexico and founding director of the Art, Research, Technology, and Science Laboratory. He has been at UNM for the past 42 years. So he basically joined UNM before I was born. Professor Angel was awarded Senior Fulbright Hays Lectureship in 1981, during which he visited IISc Bangalore. He was the first UNM Presidential Teaching Fellow in 1993. He received the Exemplary Service Award from UNM School of Engineering Alumni Leadership Board last year. His present research interests are in computer graphics and scientific visualization. He has supported graduate students working in volume visualization, virtual reality, and massively parallel computing. He has taught over 100 professional short courses, including a MOOC with Coursera, and at both SIGGRAPH and SIGGRAPH Asia. He is the author of the popular book Interactive Computer Graphics, which is used to teach computer graphics in more than 250 universities worldwide. Here at DIICT also, we are following his book for our course on computer graphics. So it's a great honor for us to be here with you. We have, I think, 8 or 9 students from DIICT, a few people from IISc Bangalore, including Professor Vijay Natarajan, and we have a few people from IIIT Delhi. I now request Professor Angel to start his session.
Well, good evening to you. Good morning to me. I'm very happy to do this. I was too bad. I'd much rather be there in India. We very much love India. We've been there about 10 times, and the most recently we were in Kerala a year ago before all of this happened, and now it's getting almost impossible for us to travel. So this is pretty good with Zoom. So what I thought we do this time is I put together some information about, or some slides about, how I evolved in teaching computer graphics over many years to get to where we are now with using WebGL, and I want to follow that with some of my favorite examples that I've done in my classes, and maybe it'll give you guys some idea of projects that you might want to do. So let me switch over to sharing the screen, and I'll go for about half an hour. I'll try and talk. I talk very quickly. I'll do about half an hour on this presentation, and then maybe we'd have half an hour for discussion and questions and things. Okay, so let me switch to sharing the screen. And now let me start this. Here we go. Okay. So that's looking good. Okay. So what we talk about first is just how things evolved in terms of the kind of software and hardware that we've used. Now, one thing to sort of point out here is I've really evolved, because I didn't start off in computer graphics, and having come from an imaging background, where I did image processing for a lot of years. And even before that, I was more of an electrical engineering systems and control person that started doing 2D problems. But when I first got challenged to teach computer graphics, I was kind of convinced it couldn't work, because at that time the computers were very primitive, and I work with pixels and very small images because we didn't have the computation, and I couldn't figure out how we could make this go in 3D. So a lot of very fundamental things about computer graphics I was learning just as my students were learning. So you'll see sort of some of this evolution. Okay, so one of the things I want to point out is I started teaching computer graphics in the early 80s, I guess before most of you were born. And but the basic ideas of what we teach in a computer graphics course really haven't changed that much. You know, the fundamentals are it's based on geometric ideas. We learn how to do transformations, both in a sort of an abstract way and a practical way. Interaction has become an increasingly important part of that. Every application we have has some interaction. And then we've moved, actually starting in the 70s and 80s, of how we got more reality into it. And that involved using lighting and shading and material properties. And this has pretty much been the same. Texture mapping came in probably a little bit in the 70s, but with the kind of hardware that we have now, texture mapping has become a very fundamental thing in everything we do. So that's the core of a computer graphics course. Depending on where you are, there'll be variations. Some things will be like curves and surfaces are more important to some people than they are to others. The other thing I probably should note is that when I started teaching computer graphics wasn't taught in that many places. It was a few places that were really known for computer graphics, like North Carolina and Stanford and a few others. But as time evolved and we got better hardware, everybody was teaching computer graphics. But what I wanted to do was work with a course in a university where we were not producing all kinds of graduates who would do research in computer graphics, but rather a lot of engineers and computer scientists who were going to use computer graphics in a whole variety of different ways. So the importance was to get one course that concentrated on these kinds of fundamentals. Okay, and my books have been sort of taking that point of view. So there's what I was just pointing out, is that I started off with partial differential equations, started then doing image processing, and around 1982, a friend of mine challenged me to teach the computer graphics course because we didn't have anybody to do it. So in 1982, everything was pretty much theory because people didn't have the kind of hardware they could use. So the fundamentals of the two crucial books, Newman and Sproul and Foley and Van Dam, were out about this time. And if you looked at them, they were pretty much concentrated on the theory of computer graphics. They had not much software. Some of them had some very low-level software. So a big deal was if you could write to fill a triangle. You'd had to adjust every pixel. So you'd study algorithms to do those kinds of things. And the hardware was pretty primitive. The first hardware I was able to use were these terminals called DEC-GG terminals. And basically you sent out control sequences to start a line, and then a control sequence to end the line, and another control sequence to change a color. And what you see on the screen, I'm going to come back to this. This is a little bit of a fraud because we didn't have any software to do this. This is one of my students who this was his term project. And his term project was to get perspective for these cubes that didn't do anything. They just sat there. But he was worried about convergence of lines and getting it filled right. But that's all we were able to do at that time. Now it's interesting because this was my best student that year, and he then went and had a long career at Disney Animation, just retired. But you're going to see this example again later when we can actually do something with it. So let's move on. Okay, then we moved on to workstations. I was able to talk the university into buying us some of the early Sun workstations, which had 3D capability. They had some, it was the beginning of having real 3D software. And I felt that instead of having software that an instructor had to create for a class, that I really wanted to focus on the early efforts to get standardized software. And there was a lot going on during the 80s. There were two standards proposed, GKS and Core, that took different routes. They were both very difficult to use. And a lot of these early workstations had serious bugs in them. I remember on the Sun stations we had, if you let somehow your algorithm let a point escape, it would fill the whole screen. I mean, it was, that wasn't good. And then there were other standards like FIGS that came out of the CAD community. X came along so we could do network graphics. PEX combined FIGS and X. All of them were very, very difficult to use. You could get some stuff going, but they didn't work very well in the course. Then one day, one of my students, who I had a lot of students who were working at the national labs as part of their masters, and came to me, and the national labs had these very expensive SGI workstations, and he said, you know, this IISgL is a lot better than anything we used in your courses. So I started looking at that, and it was what it was. SGI, Silicon Graphics, came out with a geometry engine, which was really the first hardware pipeline. And in order to use that pipeline effectively, they needed software, and they came up with IISgL. It was a really nice combination because it had high-level functionality. You didn't have to worry about every point and every pixel, but it was close enough to the hardware that it ran very, very efficiently. Now, that version only ran on SGI machines, so it had to worry about windowing and input. What they did later was decide to have something that could run on other systems, which was the OpenGL that now we're getting to something you're familiar with, that only worried about rendering. That's basically its job, was to take some specifications of objects and materials and then render it correctly onto the screen and do it efficiently. But you still needed to connect to whatever the local operating system and Windows system was. So a bunch of libraries came up that some of you who have been doing this a little while may have seen. The libraries for X, libraries for Windows, libraries for Macs, and then things like GLUT and Glue and FreeGLUT that could run cross-platform. So if any of you is using OpenGL, the C++ version, you've probably seen some of these libraries. Okay, now we get so let me say a few things about how that evolved. OpenGL came out in 1994. It was based on this pipeline where if you basically look at what you do is you specify vertex data, then it gets transformed in various ways and converted into primitives. Then it gets rasterized and sent on eventually to output the image. What SGI also had in the pipeline was the ability to do some simple raster processing, where you could put in some data that generally became a texture, and the texture got applied during rasterization. Now, the key point here is that this was all fixed function. And these are the changes, I think, that are important for us to understand. Here is an example of a very simple, original fixed function OpenGL program. And you could still run this kind of stuff. This says, okay, now the importance here is you got two parts here. This part is saying, okay, what does a polygon look like? Well, I'm going to start a polygon. I'm going to pick a color. I'm going to then have vertex, 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 end the thing. So fixed functions do this. Then on the other side, you had to do a bunch of stuff to connect to the window system. You had to decide what the window size was, where you were going to put it on the display, create the window, and then you would render. Okay, so that was the basic thing, and you had these nice fixed functions in there. And there were other fixed functions to do viewing. I think the ones I probably should have put on here is you had fixed functions that would set up your transformations. You had a rotation function, a translation function, a function for setting up the model view matrix. All of that stuff was built in, and that was the only way to do things. Now, with OpenGL 2, you got the ability to put some simple programs into the vertex shader and the fragment shader. Okay, or into the fragment part and the vertex part. They were called shaders because they originally they affected the shading of what came out at the end. But they were very simple. They were you still had the fixed function pipeline, and these tended to look like you were writing really low level code, so it wasn't used that much except in very high end applications. Now the things really changed when we got to OpenGL 3, which was 2009. Because what happened was the people who were writing drivers, generally what was happening then is graphics was being taken over by the game industry. And the drivers were getting bigger and bigger and bigger. There were, at that time, megabyte drivers were a big deal. And so the people who controlled the industry who were selling all these game boxes said, we can't do it. It's slowing us down. It's too much memory. We want to wipe out the fixed function pipeline. And so with OpenGL 3.0, they said, as of the next version, all of those functions you used to have are gone, pretty much the whole thing. And that was called the deprecation model. And they also introduced over the years some new versions of the shader. But what that meant was by throwing out the fixed function pipeline, everybody had to write shaders. So even the simplest program that was compatible with OpenGL 3.1 had to provide a main program plus 2 shaders. And that's kind of where we are now, even though we're in my class and your class, you're working in a web-based system. It's still the same basic idea. Okay, so let's take a look now at a very simplified pipeline. So you have vertex processing, you write a vertex shader. You have a fragment processor, you write a fragment shader. The rasterizer is built into the hardware. You write an application that controls the data coming in, and that's about it. You have 3 programs that have this basic, simple structure. Okay, now just an idea. Now, the other thing that's happening these days, and I don't know how much of this you see in your class, but it's really a major thing, is that people have recognized that the GPU that is taken over. It's not just part of a software system that all runs in a CPU. The GPU is the thing that's doing all the work. And this slide is probably 3 years old, and it's just amazing that at that time, the GPU, this particular GPU that went in game engines, usually high-end Windows boards, had over 2,000 processors in it. It had 160 separate texture units. It had 10 gigabytes of memory so you can do significant imaging on that thing. And it was running at that time, they're way faster now, at 8,000 gigaflops. So this thing was sort of a little supercomputer that was being plugged in. And in fact, I used to argue with my supercomputer friends that you guys don't get it. This thing's more powerful than those CPUs you're putting in your multiprocessor machines. And in fact, that's what's happened over the years, that GPUs have replaced CPUs in supercomputers and various other special purpose chips. Okay, so GPUs really are this. We had one big supercomputer up at Los Alamos that replaced every one of its CPUs by a GPU, and then it became, like 3rd or 4th on the fastest computers in the world. Okay, so another comment about the game engine. One of the problems for us in the scientific community is that it used to be that graphics was driven by the scientific community and the CAD people, the engineering people. Now it's driven by the animation community, totally. So what we have had to learn how to do, there's a lot of my students who go and work in the game industry, a lot of them who work in the animation industry. But for those of us in science and engineering that want to do applications that are science and engineering applications, we often have to learn we're working with machines that are designed for a different community, and how do we use those things best? So that's just a little side comment on this whole thing. Okay, so let's get down to WebGL and some examples from my class. A couple of things is that OpenGL is incredibly powerful. We tend to refer to it now, the full OpenGL as desktop OpenGL. But the limitations are that everything is local. You've got to recompile it. You may have a very good OpenGL program, but you have to recompile it for every architecture that you work on. It's totally run locally. It doesn't fit in well with the kind of network world that most of us are working in. And the other thing that's happened is that the drivers have gotten larger and larger and larger. So what's happening in the OpenGL world is two paths. One is the WebGL path. The other is the Vulkan path. I think Vulkan is spelled with a K, not a C. They switch to having a small driver and making everything that the driver can do is now pushed into the app. It's the successor to OpenGL for high-end applications. The problem is that you literally can have for a given CPU. First of all, you have to understand how your GPU works. GPUs are not only very fast, they have very sophisticated memory structures, so that using one optimally winds up writing what's essentially an assembly language program that you have to write as part of your application. So if you look at even the simplest graphics application in Vulkan, you might see a couple of hundred lines of code, very few of which, almost none, have anything to do with graphics in the sense that we've always been doing with OpenGL. So it's not the path that I think works with teaching. It's really the path for people who are doing really, really high-end, cutting-edge games, particularly. The other path is what happens at the low end. Well, OpenGL ES, which preceded all this web-based stuff, was still based on 3.1. The idea was to put it on low-power embedded devices and not have to support the whole OpenGL. But what happened is, especially with cell phones, is people realized, hold on, I have to come back here. People realized that this works in a network environment. And so WebGL, which is meant to work over the web, is based on OpenGL ES. And the simplest statement is it's a JavaScript implementation of OpenGL ES. Okay, pretty much identical. Now, why JavaScript? JavaScript because it's the language of the web, and what it lets us do is integrate that with other web-based applications. And so for an awful lot of people, this is a wonderful combination. I don't know how difficult it is for you people. You can maybe say later about learning JavaScript. It's always been somewhat controversial in the computer science community, at least the academic computer science community, but I think that's changing pretty rapidly. So why I teach it with it is you're hopefully all seeing that in what you do. It's cross-platform. I just write it once, it runs everywhere. Easy to get started. It's pretty fast to change things. A lot of tools out there. Just a whole lot of nice things. Integrating it with other web apps is very, very easy to do. And the performance, you don't take much of a hit because even though you download it from someplace, but it's going, if you have your app somewhere on a server, but it's going to use the local hardware. So it's going to run as fast as your local hardware lets you do. Okay, so what you have to learn a little bit, I assume you guys are in the middle of this now. You have to know JavaScript, a little HTML, and execution is a little bit different in a browser than it is in that. And you do have to do some interactivity. Okay, so that's the end of my rant about how it got going. Let me show you some of my favorite things I've done in my classes over the years. Okay, so here's a typical, so generally what I do is I do a project-based course. I give out 3 programs that everybody does. There's a lot of variation that they can put into them. And then they do a term project that they pick. I give some hints and they pick one or come up with their own. Okay, so the first one I do is just to get them started. I do it in 2D usually, is I start with a triangle and I introduce the concept of twist, where twist is rotation, but you do more rotation the further you are from the origin. So you can think of the origin as being here in the center. And I say, I want you to do twist, but you can't really do twist unless you tessellate. So now when you tessellate, you run, you can go through recursive algorithms to tessellate a triangle. There's a lot of neat things you can do here. But then each one is rotated in 2D, but rotated depending by amount depending on how far you are. So you get these nice curves, and some of the students get really into it and do a lot of nice variations of it. But that's a real basic, acceptable solution for their first programming project. So now they understand the basics, they know how to write a program. Now we try and move to 2D. And a lot of what I do for my second project, to 3D, a lot of what I try and do in my second project is get them to add significant interactivity. So I gave them this problem. This is a very good one, where I said, we've started doing transformations. We haven't done shading yet. So what I say is, do a little CAD program. This is a geometric CAD. They can do a circuit program if they want, but I sort of push them to this way. So they'll do a little 3D. They'll learn to use some interactivity here, like sliders here, other ways. There's selection over here. And this is totally a WebGL program. So he can create these shapes, move them around, and do it. So that's a real nice one for that second exercise. Okay, now in the third exercise, the idea now is I'm getting towards the middle of the semester. And what are the key things they should know by then? They should know about viewing. They should know about transformations. They should know a little bit about modeling. And they should be pretty good at interaction. So I try and come up with a project where they can, I have two favorites I'm going to show you, where they can incorporate these four things into a single project that they can do within about 3 weeks, maybe 4 weeks. Okay, so here it is. Now, this is, I can't run this one. I'm going to run some other ones. I don't know where the code from this went, but I have them do a 3D maze. And this is a 2D version. Well, this is sort of a 3D, looking on above, yeah. So the idea is sometimes I start them with the first project of making a 2D maze, a maze where you can go from so all you have to do is draw lines, but it's a good, I want them to use their computer science, because a lot of times they go through computer science for 3 years and we're really stressing them, we're beating them on the head. It's algorithms and it's theory and it's programming. This is fun. So they can combine all of these into doing a 2D maze. And then when they get to the third project, I say, I want you to make it into 3D. And then I'll give you some examples in a minute. This one is a very basic one where they extrude out the sides. And then you have interactivity to let you walk through this thing and not crash through walls. A lot of flexibility here I'm going to show you. So the first thing is the 2D maze. And the basic idea here, this would be this first assignment. You just start with an array. One way to do it, you start with an array, and it's really a graph search problem. You start looking for paths by knocking walls out of this complete 2D array, and then until you till you get a path from every cell to every cell, and every cell's been visited and has a path to every other cell. Okay, so we'll show you some more of that. So then when I get to the 3D, they start with the 2D say they connect them all by removing walls and do it. There's a lot of ways to get mazes. This is a maze where there's one path from any cell to any other cell. Okay, then they extend it to 2.5D by just making the walls go up. Okay, and actually some of them done 3D mazes, which are really interesting. But these 2.5D ones are pretty straightforward. They pick an entrance and an exit, and then they have to have some way of interacting with it so they can walk through it. Okay, so here's a couple of examples. Now these are two very good ones. Since we were doing texture, they both use texture to get a floor, a ceiling. This guy has a ceiling. This guy has it out in the open. Let me see. I think I could run these. Yeah. So here's one where, okay, you can move forward. He won't let you go through the wall. You can turn right. Keep turning. See, there's the entrance where he came in. Here's another one, Oh, let me turn right. Let's see what happened. No, I didn't go too far. Here's another place. So this is a pretty good one. And it's a lot of fun to do. Let me go to the next one. Let me kill this guy. Okay, this guy, they each have to figure out their own user interface. So in this one, let's see, I think I used the arrow keys. Notice, see, in this one, he's not doing all 90-degree turns. He's able to do incremental turns, which makes things, see, he's on the outside here, so I got to get him inside, come back here. This makes the interaction a little harder. But if you hold your finger on the key, you can go faster and slower. Now you can turn. Oh, not quite far enough. So anyhow, you get the idea. He's used a lot more interesting texture mapping here. Now I can turn. Oh, dead end. Oh no, there's a way. So now we can go down here and so on. So these are really fun examples. I gave a talk, I know it was a year or two ago at SIGGRAPH Education. They have a sessions now on groovy assignments. What are your favorite assignments? And I did this one for them. But I have one I like even better, which I've done. I said I'd get back to this. Rubik's Cube, okay? This is a great assignment because to do this well, first of all, the interface is kind of interesting because you want to be, what happened here? Okay. You want to be able to look at different sides of the cube, but you also want to be able to rotate different sides of the cube. So you got a lot of possible interactions here going on. Let me rotate. Here's rotate one way. I think this rotates. Does this one rotate? Like this. Now I can go back and look at it. I have here's the scramble function to get a new one, a new one in here. And so this is a great assignment. The hard part of this for the students, besides the interaction, is the transformations. If you don't really understand transformations, trying to rotate where each one is rotating a different amount and they're all off center is really tests whether people understand. So I love this assignment. And so going back to the first one where they could only display a cube, they couldn't rotate it. Now they can do this. The only reason I don't give it anymore is if you type Rubik's Cube WebGL into your browser, you're going to find lots of solutions that are already there. So I haven't been giving this one lately, even though I think it's a wonderful, wonderful assignment. So, okay, so let me finish up showing you a couple of my term projects. Okay, let me get rid of this one. So here's just a couple of term projects. This one is an actual 3D CAD. It's a solid modeler. So if you look up on the top right there, you see that it actually you can put shapes together where it'll take the shapes are solids and it'll remove parts of it. Nice interface here of doing it. That's one. Here's one of my real favorites. This one is some of my students are interested in algorithmic animation. And so what they do here is take an algorithm they've been studying in their advanced algorithms course and do it. This is a Voronoi diagram. I don't know how many of you know what that is. What it is you start with a bunch of points. They're down here. I don't know if you can see them. And every polygon here is based on this is the one closest. This point here is closest to this one, so it's green. But this point here is purple because it's closest to this center of all the points. Okay, that's the Voronoi diagram. And he animated it. So the center points are moving around. Watch this. The center points are moving around. That's just a fun example. And you could just see that thing dynamically changing the diagram in there. So that's a really fun project I've always liked. Okay, what else do I got here? Okay, I got him. No, stop that. Go here. Okay, I just want to show you a few others we've done where we're using a lot of things we're interested in. Let me skip over agent. Well, we do a lot of agent-based modeling in New Mexico. So we deal with large particle systems. And let me just show you a couple here that we've done. These might be on my website. Let me see. Oh, no, come back. Oh, here it is. These are particles, two groups of particles that are moving around randomly, but they're not allowed to go in a center region. So it's just a little simple thing. And so they wind up surrounding, there's a box I said you're not allowed to go into. So I keep generating more and more points, and you'll eventually see what's on that other one. They won't go into this box in the middle. So that's one. Let me show you another one. Get rid of this guy. Let me show you another one. This is more particles. So here's very simple little sprite. Now we use point sprites a lot. This one shows them where they're not allowed to touch each other. So they form these beautiful patterns by avoiding each other. But there's not really much randomness in there, just a little tiny bit. The other one, this one I think is kind of cool. You might want to do. These look like hundreds of thousands of shaded spheres running in real time over the web. One of the cool things about this is there isn't a sphere in there. They're all point sprites. These are actually 2D little point sprites for doing cloud rendering that have been shaded to look like spheres. And this runs, I've run this with hundreds of thousands at full speed on this is running on a standard iMac. No slowing down at all. So it just shows you how powerful the whole thing is. Okay, back to this guy. Okay, so this is about it. Okay, so here's the new edition of the book. It's gone to WebGL 2. Few minor changes in the code. If you go to interactivecomputergraphics.com, I have both WebGL 1 and WebGL 2 versions of the standard ones, plus some extra ones that only run in WebGL 2. So for example, 3D textures is a big thing in WebGL 2 that it's supported. So I have some visualization examples in there. Some other apps that are in there that I don't think are in the 7th edition, like shadow mapping and projective textures are in there. And there's a little information just to finish up about 3JS. 3JS is a very powerful scene graph that runs on top of WebGL. So you don't have to worry necessarily about writing shaders, setup, and a lot of CAD people just love it. It's very powerful. It's worth looking at. I don't like to teach with it at this class for computer science and computer engineering because I want to have people understand what's going down underneath and have to write their own shaders because that helps you understand what's going on and gives you a lot more flexibility. But if you're doing apps and you're generally just looking at an app to do some visualization of objects, geometric objects, design CAD, 3JS is pretty amazing, and it's all open source out there. Okay, so let me stop here, go back, I'll stop screen sharing, and be happy to answer any questions or whatever you guys want.
Great, thanks, Professor Angel. This was amazing. In fact, as I shared with you over email, I have always taught with OpenGL, which is now called Desktop OpenGL. And this is the first time for me teaching using WebGL. So it is a learning experience for me also. But I think that the students probably are picking up JavaScript better than me. I think they have more experience in JavaScript.
That's a problem for us older people.
Yeah. So I think they already are pretty comfortable with HTML and JavaScript. So I think it's not an issue for them. It's more a challenge for me as a teacher.
What kind of projects are they doing?
So we did this tessellation assignment. That was one of the assignments in one of the labs. Then they have completed one project so far in which they created a scene of the campus. So we are all living away from our university campus right now.
Yeah.
And so the project was to recreate some scene from the campus. It could be from their residence or from a classroom or from the open air theater. And different students chose different places to show. Should I share them with you? Would you like to see?
Sure.
Let me see. I have the first version. I don't know if I have the latest version. Let me just see. Yeah, I do have some. One second. So while I do this, other people in the call, please feel free to ask any question. You may unmute yourself and ask. Yeah, I think my system is just about to hang up. Not able to take the video call and other things. Yeah, so what we did was they had to create a scene of the campus, and there were some additional marks, some bonus marks for adding sound and animation. Even though we had not done it in the course, the intention was for them to, try it out on their own, learn it on their own, and then add. And many of the students they added some sound and they created some animation. In fact, one of them created a beautiful fractal tree. I'm just trying to see if I can find that now, but my machine is not helping right now. Yeah. So I think Hitesh, if you have your machine right now, can you, Hitesh and Vishal, can you show the tree, the fractal tree, if you have it right now?
Yes, sir.
And as I said, we also have some students from IISc Bangalore and from IIIT Delhi. Please jump in. You can raise your hand or you could write to me in chat. Uh, please go ahead.
Sir, I'll share my screen.
Yeah.
Yes. So,
There you go.
yeah. So this is actually my hostel room, which is probably my favorite from our campus. So for the tree, I used fractal. I created with fractal. It's a fractal tree, and
Yeah.
when I'm creating the branches, I'm just randomly changing the angles, so it looks like a real tree.
Yeah. Very nice.
Yes.
Thanks, Vishal. And Hitesh, can you also show?
Yes, sir.
So Hitesh made a lot of grass. He showed a part of the campus, which was, yeah.
It's our library, sir.
Yeah.
So, so the trees and the grass and the shading of the tree and all that.
Yeah.
This is,
Okay.
Thanks, Hitesh. Okay. So, guys, do you have any questions?
So this is Vijay. I had a quick question. So I hear you when you said that WebGL and the reasons for choosing WebGL, right? But so if I were to, so would there be a reason for choosing OpenGL to to teach or to introduce graphics to kind of a specific, like a specific subset of students, let's say students where you want to do, with whom you want to do high performance graphics, or I'm just trying to think of reasons where.
Yeah, I think that's right. If you had a specific application, or you had a group of students that wanted to work on high-end game engines,
yeah,
then I'd switch them over to even try to run them on Vulkan, and it's, the other thing that's happening is that, the big market now for GPUs, it turns out, is the AI industry. They found that, and so, so then there's the whole thing of having a course that might use some of the software that's specifically designed to work on, and it's not based on, it doesn't have anything to do with graphics to use. And so, the problem is, I still think it's probably easiest and best for more students to start with a WebGL based course and then have other courses that come out of that.
Okay.
Okay. And there's a bunch of standard, also with VR, there's a bunch of open VR standards coming out.
Right.
There's a whole bunch of things happening, but it sort of depends what how many students are in your university, what are their career paths. And I think for most of us, we need a beginning course, because I think what we do in this course, you could teach it with sophomores, you could teach it, it doesn't require much. And do your students know JavaScript when they come in?
So I mean, for me, it's kind of unique. We teach only master's students. We don't have undergraduates.
Okay.
So for me, it's a blend of introducing graphics and trying to do research work with them. So I move over to some research papers, focus on some, let's say, data structures, or
what is it? Is the department called computer science?
It is a computer science department, yes.
I forget what, I don't think it was computer science long ago when I was there.
The name is kind of interesting. The name is computer science and automation.
That's okay.
So the origin comes from robotics controls. So I think our department, for example, offered I think a pattern recognition and a neural network course in the 80s, when people didn't know about neural networks.
Well, then a course that focused on GPUs would really be a good course.
Right. Yeah. So we do have courses now on GPUs, but taught by the architecture folks.
Yeah. The thing I was going to say is that the whole JavaScript thing, the faculty were more opposed to it than the students. The students don't learn JavaScript where we are. They still start in Java. They do C, C++, they do a few other kinds of languages. To them, it's just another language. Give them a couple of days, they'll do it. Yeah. It's the faculty, especially the older faculty, that just have, and JavaScript does have a bad history, but still, it's the people I work with here that are doing very high-end things are looking at a whole bunch of sort of JavaScript variations like AgentScript and other things that they love. Okay. But the arguments that people used against it just aren't valid anymore.
Right. So in our class, we have actually some projects where they do WebGL, but that's where the application kind of requires the use of WebGLs. For example, visualizing data that's available off the web, trying to use WebGL to develop interesting visualizations. Okay.
And there's some database stuff for getting databases across in WebGL applications that are out there.
Right. Yeah. Even there. Exactly. Right.
Okay. Thanks, Vijay. In fact, I also had similar concerns when I started teaching using WebGL. So in fact, I wrote till about last month. I was not sure, and I sent an email to Professor Angel, sharing my dilemma with him whether to continue using OpenGL or to switch to WebGL. And his response kind of made the decision for me. One of the things which he wrote was that students love being able to show their applications on mobile phones, being able to share it with their peers and family members if it's on the internet. And this was what I'm teaching is anyways an introductory course in computer graphics. So for that purpose, I felt that WebGL, is perfect. Okay, so we have a question from Udvarg Chaturvedi. I am unmuting you now.
Hello, can you hear me, sir?
Yeah.
Yes.
I just had a quick question. Which aspect of modern computer graphics, like computer graphics as it is in today's age, is most interesting to you? Maybe that you find very flashy and attractive, or maybe something that's interesting.
For me, I mean, I since I'm I don't teach regularly now. I've been sort of retired, but I do a lot of things. I mostly the only project I work with are friends. If you look at the cover, let me show you this. This is interesting here. Actually, these are people that I work with here. Some of them are my ex-students. Some of them are been here a long time. What you see here in this image, this is actually Santa Fe. What you see up here is a cloud-based rendering. So you just show the cloud somehow. Then what they're working on is a lot, there are big fires here now. They work with first responders and on fires. And what they're doing is trying to help people that are lost in the smoke is one of the applications by using cell phones to build up a 3D model of the terrain and the environment, combine that with maps, and then transmit that to the cell phones of people that are lost in the smoke. So they can actually look, so it's sort of an augmented reality application. So they start with these clouds. Well, they actually start down here. Here's an example down here of where people take the image with a phone, send it to a central data, gets all in real time to a central database. They wind up with a cloud, and then the cloud builds up a geometric model. So here's the mesh being built up, and then it gets rendered down to do this. So this is all being done in WebGL, and it involves millions and millions of points. And so this is a kind of application I kind of like. It's a mixed augmented reality thing, and it's actually useful out there. So those are sort of my interests now. My co-author, Dave Schreiner, works for Unity Technologies, where he's in charge of rendering, and he's very much involved with AR and VR there. So that's not to say this is the most important part, but it's just what we're personally involved with now. Actually, what I do spend a lot of time with, because the schools are closed, is I'm working a lot with kids in the early grades, 4th and 6th grade. So these are like 8 to 10-year-olds, and we're working with them to teach them some computer ideas. And I have some little robots I program. Nothing to do with OpenGL, but it's a whole different audience.
So actually my son is 8, and we have just started teaching him Scratch, which is this visual language developed by some people at MIT.
Oh, Scratch. I'm using Scratch-based stuff to program microbits. Here, let me show you. These are one of the robots that we program with, essentially with Scratch. Okay. And it uses the microbit card here, which I'm teaching the kids to use. The card comes out. You can program this with a simulator, and then just plug it in to the robot and download the code from the web. And I have these things running around. They avoid each other and various other things. So this has been a lot of fun.
Okay. So they actually see the output is basically physical. They actually see a toy roaming around, following a path.
Yeah. But it's interesting from the teaching point of view that I was working with projects in the schools for a bunch of years where we were saying, what's the best way to teach kids to start programming and do algorithmic thinking? And Scratch is one. It's
Okay.
we were using agent-based models as a way to do it, which were fun to do, but the kids do best starting with Scratch, it seems.
Okay. I saw this very famous lecture, the last lecture by Randy Pausch, and I think he
Oh, that's a
mentioned
very
that-
famous lecture.
yeah, yeah. And I think their group developed Alice, which
Yeah.
was also to introduce programming to kids. Have you tried using that? I mean, which one is better or easier for kids to pick up?
I don't, I haven't followed that. I don't know. I think it's still out there being used, but since he passed away, I don't see the thing. I think there's a small Alice community, but I think slowly Scratch has become the major one
Okay.
for kids.
Okay. Yeah, I think even in Minecraft, there are these routines. Minecraft education is there. And there
Yeah.
also there are these routines based on Scratch-like structures.
Yeah.
Okay. So I think we'll just take one more question. This is from Amok Gulati, and then we'll wind up the session.
Hello. Good evening.
Hello.
Am I audible? Hi. I'm sorry if my question is a bit naive. I really only have about 3 weeks of experience with computer graphics.
That's fine.
I mostly come from a deep learning background, and that is where I got a slight exposure to computer graphics. There were a few techniques, deep learning techniques, which were being used to simulate the water or something like DLSS by NVIDIA. So that's how I developed my interest into this course. But all these techniques are not actually in the course. And do you think there is a future for deep learning and computer vision going ahead? Should I really be working with it, doing something
Should you, wait a second, what should you do in the future? Work with?
should I try looking into deep learning and some sort of combination of deep learning and computer graphics?
Yeah, I'd probably say two things. That's one of them. The other is that, the other approach to computer graphics is ray tracing. And if you're doing things like water and waves and pads, then you might want to look. I think at the very end of the book, I have some pointers to ray tracing and photon mapping and things like that. And that's the other approach. And there are people who start with that. But I think if those are your interests, you should look at that and follow up on that path.
Thank you. Thank you.
I think in your book also early on you say that ray tracing is another approach, but in your book you don't follow it because it's not so conducive for interactive applications.
Not yet. I mean, we keep saying it's almost there, but mostly I think the book is getting bigger as it is, and it would just get too big if I started doing those things. But then, what's happened over all these editions is I get instructors who say, if you don't put this in your book, I won't use your book. So we wind up adding little things here and little things there. And but I think the way it is, it makes for a nice course as is. So, but
Yeah. In fact,
I always like to hear comments back. So keep me in the loop.
Yes. I think it's a great book. I'm planning to cover the first 7 chapters for sure, which includes texture mapping. And then I personally like the hierarchical modeling, and so I think I'll include that also. That's what I'm planning to do for the introductory course. I think I'll skip the implementation techniques completely.
That's become less and less important. In every edition, we make it smaller and smaller.
Yeah. In fact, I remember when I did this course as a student 22 years ago, we spent a lot of time just drawing lines.
That was the whole course.
Yeah.
What I found the first time I taught it, and I used one of the original books, and I got to that point where the best thing they could do was fill a triangle.
Yeah.
It was disappointing for the students because all of those movies were coming out, with all this incredible graphics, and they never got to understand how any of that was done. That's when I started doing the top-down thing of saying, let's start with 3D, and we could do that stuff later at the end.
Yeah. Perfect. So I think we are a couple of minutes past 9. I mean, 9:30 a.m. your time, and thank you so much for having this session, talking to us. And
okay. Well, maybe we can, at the end of your course, I could see the projects they do.
I would love that. Yes, absolutely. Absolutely.
This is so easy to do. So
Yes, yes. Perfect.
Okay.
We'll do that. We'll do that.
okay. Well, I enjoyed this a lot. So thank you.
Professor Angel. Thank you.
Thank you for inviting me.
Thank you. Thanks everybody for joining. Thank you.